Here we go. Can everybody see my screen now? Okay, good. All right, in an electron microscope, electrons are accelerated at great velocities. Calculate the wavelength of an electron traveling with a velocity of 7.0 times 10 to the power of 3 kilometers per second. And it also gives us the mass of an electron. So here we're given the mass of the electron, and we're given the speed of electron, and we're asked to calculate the wavelength. So we need a formula that relates wavelength to mass and velocity, don't we? And we saw that equation, which is wavelength is equal to Planck's constant divided by mass times velocity. And so we saw that any kind of object can have a wavelength associated with it. However, the only kind of wavelengths that will have any meaning for something that has mass and a velocity will be for very, very small objects, right? There's even a problem that's in my slides where I went over, calculate the wavelength of a tennis ball or something. And a tennis ball does have a wavelength associated with it. It's got a mass and a velocity when it's, hit with a racket. However, the wavelength is so small, it's basically immeasurable. So since we're dealing with an electron, we should get a wavelength that makes some kind of sense, something that would be measurable. So let me show you. We're going to say the wavelength is equal to Planck's constant, 6.63 times 10 to the power of negative 34 joules times seconds, divided by the mass, which is 9.1 times 10 to the negative 28 grams, which I need in kilograms, don't I? So I'm going to have to convert that to kilograms. So if I have 9.1 times 10 to the negative 28 grams, I know that in 1,000 grams, I have 1 kilogram, like that. So I end up with, I'm just doing this in my head, 9.1 times 10 to the negative 31 kilograms. There we go. So I have kilograms. There we go. And then my velocity is 7.0 times 10 to the power of, no, I need that in meters per second. Shoot, a lot of conversions to do here. Okay, let's do this one. So we have 7.0 times 10 to the power of 3 kilometers per second. I know that in 1 kilometer, I have 1,000 meters. So these cancel. So I end up with 7.0 times 10 to the power of 6 meters per second. There we go. Now my units work out, times 10 to the power of 6 meters per second. Like that. And if you're wondering, why did you convert that into kilograms and why did you have to convert that into meters per second? Well, if you've ever taken physics before, you know that a joule is equal to a kilogram times meter squared per second, like that. And so when we plug that value in here, we end up with our wavelength, which is going to be in meters. And we end up with 1.0 times 10 to the negative 10 meters. So here we go, D, 1.0 times 10 to the negative 10 meters. Question number 11. Which of the following, if any, is the correct ground state electron configuration for a lead atom? So I'm going to pull my periodic table off of my bulletin board here so I can follow along. And let's work out the electron configuration for lead. And you notice that we do have the shorthand here. So if we look at lead, so we're looking at lead, which is element number 82. The noble gas that precedes it is xenon. So immediately we can eliminate B like that because that starts with krypton. So what comes after xenon? We have 1, 2, 3, 4, 5, 6. So we have 6s2. Now remember that after a 6s, right, after barium, we go down to the lanthanides. So we go from 6s down to 4f. How many possible F electrons can we have? We can have 14. Then we come back up to the transition metals, back up to 5. We have 5d10, and then we get back into the p block where we have 6p, and then we have 2 electrons in there. So this should be the electron configuration. No, I didn't do this one ahead of time. Which one is it? You guys have better eyes than me. Looks like it's A. Does everybody agree with me? Yeah, good. Thanks, Christina. Good. Okay, there we go. So that's the electron configuration of lead. Not too bad. Question number 12. Which of the following sets of quantum numbers is not possible? You know what? I'll throw this out there to my students. Is there anyone here that looks jacked up to you guys? There's my eyes drawn to one right away. Thanks, Christina. Christina, can you tell me what the problem with B is? You're absolutely right. That's the one I'm noticing. There seems to be an issue.
Because L is 0, so ML can't be higher than L. It has to equal.
When L is equal to 0, the only possible value of ML is 0, right? It can't be anything else. So it can't be 1. So the answer is B. This is a classic question for the final exam or for an ACS exam or a standardized exam. They love to just give you sets of quantum numbers and then you tell, which one of these is wrong, right? You just pick out, an inconsistency. Great. Thanks, Christina. Question number 13. Which of one of the following sets of quantum numbers represents an electron with the highest energy? So highest energy. Well, if we look at A, you have n is equal to 4 and you have L is equal to 0. Remember that when L is equal to 0, 1, 2, or 3, you're dealing with an S, P, D, or F orbital. So in A, if we have n is equal to 4 and L is equal to 0, that means we're dealing with a 4s orbital. In B, we're dealing with a 4p orbital. No, sorry, 4d orbital. My mistake. Let's see, what else do we have here? In C, we're dealing with a 3d orbital. In D, we're dealing with a 5s orbital. And in E, we're dealing with a 4p orbital. Okay, got all those right. So I see what they're doing here. So the question is, which one of these is the highest energy? It might be a knee-jerk reaction to say, hey, it must be D. It must be the one that has the highest principal quantum number. But hold on. If you go to a 5s, so 5s starts on rubidium, element number 37. It goes from rubidium to strontium, so that would be 5s2. Then from there, you go to what? You go to a 4d. So a 4d is actually higher in energy than a 5s because as we add electrons, we get into higher and higher energy, right? That's the Aufbau principle. And so the answer are the 4d electrons. So we could summarize that by saying the energy depends on N and L for a multi-electron atom, not for a hydrogen atom, but for a multi-electron. Okay, let's move on to question number 14. List the following sets of quantum numbers in increasing energy. This is pretty similar to the last question where we have L is equal to 0, 1, 2, 3. So we have an S, P, D, or an F orbital. The first one is N is equal to 4, L is equal to 0. This is a 4s orbital. The next one is a 4d orbital. And the next one is a 5s orbital. Well, I already explained to you in the last question why a 4d is higher energy than a 5s. And so 4d is going to be the highest energy of all these. Then if you're comparing a 4s and a 5s, a 4s is going to be the lowest. So it goes 4s will be the lowest, and then 5s would be somewhere in there. So what are their numbers? So this would be 1, and then 2 would be the king of the castle, and then 3 is somewhere in the middle. So which one is that? That's C. There we go. So we go from 1 to 3 to 2, which is the highest energy. Okay, number 15. We did a question like this in our practice problems. It says, what is the maximum number of electrons that can have the following sets of quantum numbers? So I'll throw this out there to my students. We have N, we have L, we have ML, and we have MS. Does anybody have an idea what the answer to this one would be? Thanks, Christina. You're absolutely correct. The answer is 1, right? There's only one possibility. And that goes back to a slide where I told you, you know, it's just like mailing a letter. You have the name of the person, you have their street address, you have their city, you know, you have their postal code or zip code is what we call it down here in the States. And so every electron can only have one complete set of quantum numbers. Or to phrase it the other way, a complete set of quantum numbers can only represent one electron in an atom. So the answer is 1. It's kind of just a more of a conceptual question than anything, that one. Question number 16, a possible set of quantum numbers for the last electron added to complete an atom of gallium in its ground state is, well, we're going to have to figure out what the electron configuration of gallium is. So gallium is element number 31 on the periodic table. It comes right after zinc. So Z is equal to 31. The noble gas that precedes gallium is argon. So the shorthand configuration is going to be argon. After argon, we have 4s2. Then we have 3d10. And then we're back into the 4p. So we have 4p1. Therefore, this is the last electron added here. Now we need to come up with a set of quantum numbers, which are N, L, ML, and MS. Well, if it's a full set of quantum numbers, the N is going to be 4. The L is going to be 1. My ML, if it's the first one, I'll give it a value of 0. And my MS is going to be plus a half, like that. All right. Possible set of quantum numbers. I notice there's something funny about this question too, or something I don't like about it. I mean, it's the way the question is worded. It says a possible set of quantum numbers, and this is the only one that's possible, right? None of the others are even remotely possible, because here you have a 4s, here you have a 3p, here you have a 3p, and here you have a 4d. So none of these are right. The only possibility is C, which is a 4p. So that's definitely the right answer. The only thing I don't like about this answer is that you would think that the first ML value you would assign would be -1, but whatever. I guess it's a possible answer, and so it's the only possible answer. I don't see how you could mess it up. All right, number 17. How many orbitals are allowed in a subshell if L is equal to 2? Well, this one we know about orbitals. When we have a subshell that's L is equal to 2, we have L is equal to 0, 1, 2, 3. We have S orbital, P orbital, D orbitals, and F orbitals. So we're dealing with a D orbital. How many types of orbitals do we have that are D orbitals? Right? We looked at them. We looked at the pictures of them. I didn't ask you to have to be able to draw them or anything, or to label them. But does anybody remember how many types of D orbitals there are? Not a trick question. Right, if my L is equal to 2, then my possible values of ML are -2, -1, 0, +1, and +2. That is 1, 2, 3, 4, 5. Exactly. Thanks, Christina. There are 5 orbitals when my L is equal to 2. Let's move on to number 18. An orbital diagram for the ground state of carbon is, well, let's start by writing out the electron configuration of carbon. Carbon is element number 6. We have 1s2, 2s2, and then we have 2p2. Well, how many types of 1s orbitals are there? There's only one. How many types of 2s orbitals are there? There's only one. How many types of 2p orbitals are there? There's 1, 2, 3, right? The 2px, the 2py, and the 2pz. So we'll just label those the 2p. If I have 2 electrons in my 1s, one's going to be spinning up, the other one's down. If I have 2 electrons in my 2s, one is up, one is down. Based off of Hund's rule, I do not pair my electrons up like this. So A is not the right answer. Right? Hund's rule is like what I call the bus rule, where the next electron is going to go into the next orbital because we want to have the maximum number of parallel spins. And so that means that D would be the correct answer. There we go. Number 19, which of the following is diamagnetic in both its ground state and in all of its excited states? So diamagnetic means all electrons are paired and that it's not going to be attracted to a magnetic field. It's going to be slightly repelled. So we can put that in here. All electrons are paired. So we have no unpaired electrons. All right. So which one of these has all of its electrons paired up? Well, in the interest of time, instead of me writing out the electron configurations for all of these, we could just kind of take a quick look at them. We looked at the exception of copper during our last lecture, and I explained to you why the electron configuration for copper is argon. And then since copper is the 9th element in the D block, you might think that it's 4s2 3d9, but in fact it's 4s1 3d10. Okay, it's actually this, and so we end up having an unpaired electron in copper. If we go to zinc, we have all of our electrons paired in zinc, which is argon 4s2 3d10. However, it says also in the ground state and all of its excited states, right? What's an excited state? An excited state would be when we promote an electron from the 3d orbital into a 4p orbital, which we can do because they're so close in energy. If we look at magnesium, the noble gas that precedes magnesium is neon. And so we have neon 3s2. All of the electrons are paired. However, we can excite an electron into the 3p orbital. We could put an electron into there because it's in the same period, much the same way we could with our zinc. However, with neon, and follow along with me here, neon, if I look at the noble gas that precedes neon, it's helium. After that comes 2s2, 2p6. So in the 2s orbital, I have both electrons paired, and in the p orbital, I have 1, 2, 3, 4, 5, 6. And so the reason why it's neon, even though it appears as if all the electrons are paired in zinc and magnesium, the difference is this. The difference is that there are more orbitals available in the same period for zinc and magnesium. For neon, there are no more orbitals that are available in the same period. There's nothing past the 2p in the same period. So if I tried to excite an electron to put it in a higher energy orbital, there's nowhere to go. It would have to increase a quantum number and go to the next period. Whereas with these ones, you can just go to an orbital in the same period, and that is an excitement that's allowed, okay? And since we can't excite any electrons in the neon atom, it is diamagnetic because all electrons are paired. So the answer is the neon atom. Okay, question number 20 is a long one. So I gave myself an entire sheet of paper, I think, to work on that one. So let me walk you through this one. It's not that bad once you understand what's going on. And I think I assigned a problem similar to this in the practice problems in the textbook and put the solution up on D2L. So let's take a look. It says a single pulse of a laser yields on average 5.00 times 10 to the 18 photons, and they have this wavelength. Okay, good. If melting ice to water at 0 degrees Celsius takes 6.01 kilojoules for every mole, what's the fewest number of laser pulses that I need to melt 10 grams of ice? Well, here's the way I solve the problem. The first thing that I think of is this. If it takes this much energy to melt this much ice, if I know the amount of energy in kilojoules per mole, then the question for me becomes, how many moles of ice is this? All right, that's where I start. So I say I've got 10.0 grams of ice. Ice is the same thing as H2O, right? Ice is just H2O. So let's say we got 10 grams of H2O in the solid phase. And I just divide that by the molar mass of ice, which is 18.01 grams per mole. And this is just a very quick calculation. We've seen this many times in the class. And this tells me the number of moles of ice that I have. So I have 0.555 moles of my ice. Okay. Now I can tell myself, or I can figure out how much energy it takes. Right. The amount of energy required is going to be 6.01 kilojoules per mole, and I'm melting not a whole mole, I'm melting 0.555 moles. And so moles cancel, and I know how much energy it takes. Now I can wrap my head around it a little bit more because I've got 3.34 kilojoules of energy to melt 10.0 grams of ice. So that's how much energy I need. But I've got a laser that shoots a wavelength of 633 nanometers. That's my wavelength. And so I can also calculate the energy of one photon, right? Because I told you that earlier on, when you calculate E is equal to hc over lambda, this energy is per one photon. So let's work that out for that wavelength of energy. I've got 6.63 times 10 to the negative 34 joules times seconds multiplied by 3.00 times 10 to the power of 8 meters per second divided by my wavelength, 633 times 10 to the negative 9 meters. Let's check it out. Meters cancel, seconds cancel, and I'm left over with the amount of energy in joules for one photon. So let's write that down, and I calculated that already, and you get 3.14 times 10 to the negative 19 joules for one photon, right? I told you that earlier this evening, that when you look at a wavelength like this and you calculate the energy, that's the amount of energy in one photon. Well, if I know that an average pulse gives me this many photons, then I can figure out how much energy I've got in a pulse, right? So one, and I'll write it down here maybe in a different color, one laser pulse has 5.00 times 10 to the 18 photons. And I know that I have 3.14 times 10 to the negative 19 joules in one photon. So we see here that photons cancel, and I'm left over with the amount of energy that is delivered in one laser pulse. So I get 1.57 joules per pulse of the laser. Well, I know how much energy I have in one pulse, and I know the amount of energy that is required to melt my amount of ice. So if I want to know the number of pulses required, it's going to be equal to the amount of energy I need, 3.34 times 10 to the power of 3 joules. All I'm doing here is converting kilojoules into joules, and you know there's 1,000 joules in 1 kilojoule. 3.34 times 10 to the power of 3 joules, and I know that I have 1.57 joules per pulse. We see that joules cancel, and I'm left over with the number of pulses. And I ended up getting 2,127. And if you go back to the answers here, you can see the one that's by far the closest to it is 2,120. And I actually must have made some kind of rounding error somewhere along the way, because my final answer should only have 3 sig figs in it, right? Anyhow, but you can see that it's definitely closest to this one, and I'm obviously not going to give you any question like this where the answer is going to be so close that it's going to mess you up or anything like that. All right, so that's question number 20. And again, I have a question very similar to this one in the practice problems. Let's move on to question 21. Where are we? Now we're into chapter 8. We're out of chapter 7 and we're into chapter 8, which is the periodic properties chapter. This one should move along a little bit faster than the last chapter.